you a practical example how you can train and develop a sequential neural network in order to predict total column ozone information. The workflow I will show you makes use of labeled training data based on a Sentinel-5P tropomi scene, which was acquired over Sicily in Italy on December 29th in 2018. And with this, I propose that we jump right into the workflow. So we are in week 5, which is related to atmosphere applications. And the example I show you is in the folder 5B, and it is about ozone concentration estimation. So if you are in this folder, you see here 3 different files. So we have a Jupyter notebook, which I already have open here. You have a CSV file, which contains the data we use for in this workflow, and also a pre-trained neural network model. And so as every example, we provide you some introduction information. As I said, we train a neural network based on Sentinel-5P tropomi data in order to predict total column ozone concentration. And the labeled data take information from Sentinel-5P tropomi level 2 data and level 1B information. This workflow makes use of the Keras API, and we train a sequential neural network. And the data we make use of is in the CSV file in the same folder, and it contains labeled data from a Sentinel-5P tropomi scene acquired over Sicily on 29th of December 2018. The file contains 2,500 row entries and 26 columns, and the 2,500 rows resemble 2,500 individual point location across Sicily, and the 26 column information represent the following information. So the column 1 to 21 are spectral radiance values for 21 wavelengths, which are sensitive to the ozone column abundance and derived from the tropomi level 1B product. Then column 22 is the solar zenith angle derived from the tropomi level 1B band 3 product. And so the same information we retrieved also from the tropomi level 1B band 3 product is the sensor zenith angle, which is in column 23. Column 24 and 5 contain information related to latitude and longitude of this specific point location, and the column 26 is the total ozone column abundance, so the total column ozone in Dobson unit derived from the tropomi level 2 total column ozone product. We also provided you additional information on total column ozone estimation with machine learning and neural algorithms, etc. And so I invite you also to have a look at this additional information. And with this, we start in the same way as we always start. We import a set of libraries which we make use during the workflow. And as I said, we will make use of the Keras API, and here specifically we train a sequential neural network. And so for this reason, we also load the sequential neural network model class from the Keras API and additional other libraries which will help us to prepare the data and also to define our model architecture. So the first step is to prepare the input and output data for training the sequential neural network. And the data file is given in a CSV, and we can use the pandas library and specifically the function read_CSV in order to read a CSV file. And as I already said at the beginning, so the file contains 2,500 rows, so from 0 to 2,499, which are 2,500 individual point locations, and we have 26 column information containing spectral radiance values for 21 wavelengths, solar and sensors, zenith angle, latitude and longitude, and also total column ozone information retrieved from the TROPOMI level 2 total column ozone product. And so once we loaded our data set, then we can define our input and output variables, which we use in order to train our neural network model on. And as input information, we use the column 0 to 23. So the first 23 columns feature the spectral radiance values, and this information we want to use as input information, so as the X variable. And the total column ozone information should serve as the output variable, which in the end we want the model be able to predict. And with this, the final column is used as our output variable, the Y. And if we have a look to the dimensions of our input and output variables, we see that we have 2,500 rows. Our input variable contains of 23 columns, and our output variable contains of 1 column, but also 2,500 rows. So the next step is to split our input and output data into training, validation and testing subsets. And so the training data is the actual sample used to train the machine learning model or the neural network model that learns from the data. The validation data is used to evaluate the model and to evaluate how well the model has fitted or was trained on the training data. And the test data is used to provide an evaluation of the final model fit. And it is only used when a model is completely trained based on the training and validation data. So we can make use of the function train_test_split from the scikit-learn library, which helps us to create 4 subsets based on the input and output variables X and Y respectively. And so the function takes the input and output data arrays, which in our case is the X and the Y variables. Then we specify a test size, and in our example we want to use 60% for training the model and 40% for validating and testing the data. And we also specify the random state keyword argument, which helps us to have a specific randomness, but also to maintain reproducibility of the specific workflow we show here. And if we evaluate the dimensions of the input and output data, we see that 60% of the input and output data is used for training, and then 40% is used for validation and testing. And then in the following step, we want to split the validation and test data also into 2 different subsets. So because on one subset we want to validate after each training cycle we want to validate the model performance, and with the other subset we want to evaluate the overall training process and the model performance. And so we want to split our validation and test subset and use 55% for validation and 45% for testing the neural network. And so we repeat the same process, but as an input and output variables we provide the validation and testing subset. And here we see then that basically from the 1,000 samples we used as a validation and testing subset, we now want to use 550 for validation and 450 samples for testing. The next step is then to normalize the input and output data. And normalization is a very common process in machine learning to bring variables that are measured in different units to a common scale. So normalization is not needed for all applications and algorithms, but for neural networks it is critical. And here we make use of the min-max scalar class from the scikit-learn library in order to scale the input and output variables. And this application specifies the minimum and maximum bounds of the feature range of each of the input arguments and scales the input and output data based on the minimum and maximum information or range. And here we specify or we apply the min-max scalar with the defined feature ranges for the input data and also for the output data. So the next step is then to fit the scalar objects to our data space. And we can fit the two scalar objects we defined to our input data and also to our output data. And we can do this with the function .transform. So we first fit the input scalar to our input data, and then we, with the help of the fitted input scalar, we can transform our training and validation and testing input data to this minimum and maximum scalar. And the same we can do with the output scalar. So we first fit the output scalar to our output variable y, and then we can transform our training and validation subsets with the function transform in order to retrieve the output variables but in a scaled version. Now we prepared our training, validation and testing subsets, and the next step is now to define and also compile the sequential neural network with the Keras API. And so the next step is now to define the sequential neural network, and for this we use the sequential class, and with this we can define our architecture. And the neural network architecture we want to define should have 23 input nodes, so one input node for each spectral radiance, and which we also use for our input data. So we have 23 input variables. This means we also want to have 23 input nodes. And then a single hidden layer, which consists of 20 neurons and one output node, which in the end reflects the total column ozone concentration. So in the end, we only have one output node because we only want to predict one variable, which is the total column ozone concentration. And so the input dimension always has to match with the number of columns of the input data. So in our case, 23. And so a sequential neural network is developed in a way that we define a dense layer which is associated with a specific activation function, and in this example we use the activation function sigmod, but there is many different possible activation functions, and so I also invite you to go to the documentation and also maybe play around with the differences between different activation functions. And then also the second layer, we also want to define again a dense layer, but only with one final neuron, and again with an associated sigmoid activation function. And the last step before we can start training the model is to compile or to configure the model, so to get all the information we need together in order to then start the training. And we can do this with the function model.compile. And for this we can specify a set of hyperparameters which help us also to evaluate the model performance in the end. So first we set the hyperparameter optimizer to a stochastic gradient descent optimizer, but this is also a hyperparameter, and you can change. There are different options, and so please have a look to the documentation, and in order to also play around with different optimizer options. Then we set the loss to mean squared error, which we want to use the mean squared error as a loss function, and as a metric to evaluate the model performance we want to use the mean absolute error. And with this we can apply the function model.compile and compile or configure the model. And now we are in a state where we prepared the training, testing and validation data set, we configure the sequential neural network, and now we can go to the step of training the model based with the help of our input training and output training data. And we do this with the function model.fit. So we use our configured model and we fit it to our training subset input and output training subset data, but the scaled ones. So we specify here in our fitting process, we specify here the input data, the scaled training subset of the input data and the scaled training subset of the output variable. We specify a batch size of 10, which defines the size of the training data subset, so 10 samples, and after each 10 samples, the weights of the networks are updated. We specify a number of epochs to 300, so number of epochs is number of training cycles, so 300 times the model is trained. And as validation data, we use our validation subset, but also the scaled validation subset data, so the input and output data. And then we train the model, but in this example, again, for training purposes, we also make you available already a pre-trained model. And this is what we do now. We go to the next step, we load a pre-trained sequential neural network and we evaluate the model performance of this pre-trained model. So one useful evaluation of the training process is always to plot the loss function and also the mean absolute error during each training cycle, so during each epoch, because if we see a decreasing trend of both metrics, this shows that the neural network has a capability to learn and train, or to learn after each update cycle. And so we see here the loss function, which has a decreasing trend, and here we also have the plot of the mean absolute error, which also has a decreasing trend. So the model has a capability of learning during each training cycle. And so the next step, after we evaluated the model performance, we can use this pre-trained model in order to predict, because this is what we want to do. We want to predict the total column ozone estimates. And we can do this with the function model.predict. And as input data, we now use our input subsets, the training subset, the validation subset, and also the testing subset. And we can also see the differences between the different training subsets. So here we predict the total column ozone estimates with the three subsets. But because we transformed the input data before, so before we can evaluate the true total column ozone values, we have to now inverse the transformation. So for this reason, we also saved the min-max scalar used for the output data, so the output scalar. And with this object, we can apply the function inverse_transform, which allows us to invert the normalization process. And the function takes the normalized predicted values and returns the converted total column ozone estimates in Dobson unit. And so this is what we see here. So we have here the predicted values, but they don't reflect the total column ozone estimates in Dobson unit. And once we inverted the normalization process, then we have the predicted total column ozone estimations in Dobson unit. And Now, this is just to see how you can also save models. So with the function model.save, you can save the Keras model for reuse later on. And as a final step, now we want to evaluate the accuracy of the model predictions. And we can do this with computing the mean absolute error between the estimated or predicted total column ozone concentration values and the true ozone concentration values for the 3 data subsets: training, validation, and testing. And we can use the function mean absolute error from the scikit-learn package, and we can provide the function the true and predicted ozone concentration values, and the result are the mean absolute errors for the 3 data subsets, what we see here. And the same process we can also repeat with other performance and evaluation metrics. So another common evaluation metric is, for example, to calculate the root mean squared error, which there is already a function available from the scikit-learn package, mean squared error. And we can apply this function and calculate for the 3 subsets the mean squared error between predicted and true total column ozone concentration values. And another very common metric is, for example, the Pearson correlation coefficient between the estimated and the true ozone concentration values, again for the 3 subsets: training, validation, and testing. And scikit-learn offers here a function R2score, which calculates the coefficient of determination. And this is in principle the square of the Pearson's correlation coefficient. And so in this cell we compute the Pearson correlation coefficient for the 3 subsets as well. And then one more evaluation performance, which is also often used, is to compare the mean and the standard deviation of the estimated versus real total column ozone values. And this is what we do here. So we have the mean information from the true total column information and from the predicted one, and also the standard deviation. So with this you also got a quite nice overview of different evaluation metrics you can use in order to evaluate the predictions from a sequential neural network. And with this we arrived at the end of the notebook.